To introduce Professor Thomas Hales. He's really, probably the reason we're here. His name is synonymous with big proof, and I think going forward, his vision will be, I think, guiding us quite a bit. Professor Hales graduated from Princeton in 1986. He's the Andrew Mellon Professor at University of Pittsburgh. He's solved many open problems, significant open problems, including the Kepler conjecture, the honeycomb conjecture. These have been, some of these have been open, I think, for a very long time, and like centuries. The thing that he came out of it with is the need to actually computer verify these proofs, and he launched the FlySpec project, which they completed this thing successfully and have published the results. And I'm looking forward to hearing about big proof from Dr. Hales.
Thank you. It's my great pleasure to be here today. It's been a number of years since I was at Cambridge. I was a student here for Part 3 Tripos in the 1980s, and I'd like to just pay tribute to two of the professors I had here. This is John Conway on the left, who's well known for his work in the theory of sphere packings and finite simple groups. And so it was from a course here in Cambridge that I first learned about the Kepler conjecture on October 22nd, 1982. On the right, I've picked another professor who may be familiar to this group. This is John Thompson, who of course was one of the authors of the Thomson odd order theorem, which was formalized by Georges Gontier. So the course I took from him was actually modular forms, not group theory. He and Conway, we were both interested in a subject called moonshine in those days, and modular forms is a significant part of that. So I want to go back and I want to talk about some conjectures today. I'm not going to solve any of those conjectures, so I hope nobody is too disappointed, but the first conjecture that I'll talk about is one that comes up in sphere packings that I've been involved with for a number of years. So this is the Kepler conjecture. So this has a very simple question to ask. What is the densest arrangement of congruent balls in three-dimensional space? And Kepler proposed an answer. It's the face-centered cubic packing, or if you want the familiar cannonball arrangement, just you put the balls in a pyramid. So you just make layers like this and then fill in the holes in the next layer, going as deeply as possible. So that was the conjecture I learned about from Conway. I want to go back and talk a little bit about the early history. Buckminster Fuller actually claimed to have a proof of the Kepler conjecture back in the 1970s. He's an architect well known for the geodesic dome, and his claim was just nonsense, but it was sort of out there that people knew how to solve this conjecture. In the 1990s, when I was first getting involved in the conjecture, a professor at Berkeley, this was a senior tenured professor at Berkeley, claimed to have a solution to the Kepler conjecture. And I thought that this proof was nonsense as well. After the paper was published, I wrote a paper in rebuttal giving a series of counterexamples to this paper, and published it in the Mathematical Intelligencer. And then this is, so that was in 1994, and about the same time, the Mathematical Intelligencer started running this advertisement. So they made a brochure saying, we're not afraid of controversy, we welcome it. If some of you know Chandler Davis, who was then the chief editor, he's very well qualified to make the claim that we're not afraid of controversy. And if you open up this brochure, what you find is the Kepler conjecture controversy. And it says perhaps the most controversial topic to be covered in the Mathematical Intelligencer is the Kepler conjecture. In the Mathematical Intelligencer, Thomas C. Hales takes on Wu Yixiang's 1990 announcement that he had proved the Kepler conjecture, and then it quotes about a page of my article in that advertisement. So we had a very public and disagreeable debate about this claimed proof. In the end, my counterexamples were convincing enough that this earlier proof was rejected. But it was against this backdrop that Sam Ferguson and I were working on our own proof of the Kepler conjecture. And it's this particular history of controversy that had us quite worried when it came time for us to make an announcement of the proof. There was no way to make an announcement of this quietly, and nobody had checked our proof when we made the announcement. And of course, I was hoping for a very speedy resolution of this issue because I didn't want to be left, in the midst of another controversy. So things did not work out as I had hoped. 4 years into the refereeing process, and so it was actually just about a month ago that the formal proof of the Kepler conjecture was finally published. And because of that, I was going back over some of the old papers, and I pulled up this referee report that came to me 4 years into the process. This referee had divided the proof into 3 phases. The first phase was sort of the mathematical part, and the second 2 phases were the computer part, sort of generating the cases and then using computers to rule out the possible counterexamples. And the referee goes through various hypothetical scenarios, including the possibility that the theory would collapse in its present form. And then the referee says, with all this in mind, one would prefer to have phase 2 and phase 3, the computer parts of the proof, checked prior to start working on phase 1 and minimize the chance that the essential work of careful reading of the manuscript might prove useless. So at this point, I became extremely frustrated. First of all, the reviewer is revealing that the work had not started yet after 4 years. Second, that the computer parts of the proof had to be checked first. And finally, that they had no plans of starting the review of the mathematical parts until the computer proofs had been checked. So it was about 6 months after I received this report that I announced the start of the FlySpec project, to give a formalization. And the long-term goal is really to just completely eliminate referees from the process. So by contrast, so this is maybe about a year later, Gertrude Bauer, working under Tobias Nipkow, started the formalization project. And they didn't, so this is still when the paper had not been published. And they weren't trying to do the full formalization, but they just picked one part of the proof, dealing with planar graphs, and made it their task to do the formalization of this one piece of the proof. And this is what I would have liked to have received from the traditional referees. Gertrude Bauer writes to me saying, I have completed a translation of your Java program into an executable Isabelle specification and tested it against the graphs generated with your program. A proof of the correctness of my Isabelle specification will also prove the correctness of the Java program. Furthermore, the generated graphs can be used for the other parts of the proof. Now, I started with the verification. Could you please help me with some questions about the algorithm? And I get very pointed, detailed questions about that part of the proof. So a few lessons from this early part of the formalization of the Kepler conjecture. First of all, do not be afraid of controversy. Don't seek it out, but when it comes, don't be afraid of it. Formalization of partial results is useful. So the lesson I see is that formalizers should be part of what you might call tactical response teams that routinely intervene in prominent, difficult, unpublished proofs. So I think there's a tendency for some people to pick mathematical gems, things that have been worked over time and time again until you have a very beautiful proof, and then those get formalized. But what was very valuable in this case was for people in this community to get involved before the paper was published and to pick out some piece that was manageable and to treat that and to help move things forward. So we all have our favorite examples that we can cite of prominent proofs that take a long time for verification, like the ABC conjecture now is, I believe, in the 5th year of review at this point. The Poincaré conjecture took 3 years to review. Hironaka's announcement of resolution of singularities and positive characteristics, maybe this is more doubtful, but there's been no official statement about that. In cryptography, there's sort of ongoing battles. I mentioned just one of them, the hash method authentication code brawl that could use some intervention from this community. While I'm still on the subject of sphere packings, the sphere packing problem has now been solved in dimensions 2, 3, 8, and 24. The solution in dimension 8 came last year. It's really quite a spectacular proof by Marina Wiazowska, pictured here on the right. She did this by solving a conjecture of Kohn and Elkies. So this is Henry Kohn standing with Marina. So in the 3-dimensional proof, there are many linear programming certificates that get verified. In the 8-dimensional proof, there's a single global linear programming certificate that gives the proof. It's a very complicated certificate that needs to be described using modular forms, but it's just a single certificate, that linear programming certificate, that needs verification. So I think this would be a nice, we finished 3. What's next? Next is 8. So it would build some nice libraries as well. It involves Fourier analysis, Schwartz functions, Laplace transform, modular forms, quasi-modular forms, and there's also a little bit of computer-assisted verification using interval arithmetic. So now I'm going to turn to some other conjectures. My second example is something that I haven't worked on, but it's part of Hilbert's 18th problem. So Hilbert's 18th problem has 3 parts. The first part was solved by Bieberbach. The third part is sphere packings and related packing problems. And then there's the second part of Hilbert's 18th problem that I want to talk about briefly now. So this is the question of anisohedral tiles. So it's best illustrated with a picture. So we all know that squares give a tiling of the plane. And there are ways to do it, like on the right, has complete symmetry, but on the left, it doesn't have complete symmetry. We have fault lines. So you can't ask whether every tiling of squares has complete symmetry, because there are other ways to do it. But Hilbert asked, the question is basically whether this picture works in general. So you take some tile with which you can form a tiling. Can you rearrange the pieces somehow so that it looks like what you have on the right, in the sense that you have a symmetry taking any tile to any other tile? So this is Hilbert's. So Hilbert liked asking these simple questions that were difficult to answer. So a counterexample was found, an anisohedral tile was found by Reinhardt in 1928. And Reinhardt, you can tell, really had a mission from the time he was a graduate student to solve this problem. He was Hilbert's mathematical assistant for a while when he was a graduate student. His advisor was Bieberbach, who solved the first part of Hilbert's problem. And in his thesis, the problem that he tries to solve is just in the plane, let's classify all the convex polygonal tiles and check whether they work, okay, whether they're anisohedral or not. And in his thesis, he found, well, the hexagons are easy. There are 3 families. Triangles always tile, so that's easy. Quadrilaterals always tile, so that's easy. But then he ran into trouble with convex pentagon tilings. And in his thesis, he found 5 families, but he wasn't able to show that there were no other possibilities. So this then became the classification problem related to the second part of Hilbert's problem, is to find all of the convex pentagon tiles. So nothing more happened after Reinhardt for 50 years, till 1968. Kirchner found 3 more families of tiles, and this became popularized by Martin Gardner in Scientific American. So Kirchner wrote that he had a proof that the list is complete, but he said it's extremely laborious and will be given elsewhere. Okay, famous last words. His classification became widely known, and as a result, people started working on tiling problems, and what do you know, more examples started cropping up, including, so this is a tiling that appears at the headquarters of the Math Association of America. It's one of the tilings that doesn't appear in the classification. And over time, more and more counterexamples were found to Kirchner's classification. So in summary, not only was Kirchner's proof incorrect, but the classification that he was trying to prove was entirely false. So as of a couple of years ago, there were 14 tilings that had been found, and these are all families. So some of these you can do some deformations and they will still tile. And then the classification was announced earlier this year, and what do you know? This was a computer-assisted proof. This is was done by Michael Rao. The proof is about 5,000 lines of C++. And if you look at the slides that he gives, he suggests that it might be a good idea of making a formal proof of this result in Coq or similar software. So he's reaching out to this group, and I suggest this is a nice problem. I think a lot of the structures developed by Gontier for the four-color theorem, such as hypermaps, should be just exactly what you need to carry this out formally. So part of this talk is inspired by a book that many of you are familiar with, Imre Lakatos's book, Proofs and Refutations. This book came out in the 1970s. When I was a freshman undergraduate, I carried this book with me everywhere I went. It and Polya's How to Solve It sort of were my guides about how to do research. So Lakatos's book talks about this dialectical process of making conjectures and finding refutations to those conjectures, going back and forth in a way that makes the growth of mathematics possible. I think this example of convex tilings fits into that. First, a conjecture, then a claim classification, then counterexamples to that, and now, again, an unpublished computer-assisted proof of the result. The next conjectures that I want to talk about. So again, the honeycomb problem is one that I was involved in directly, and the Kelvin conjectures. So the honeycomb problem is a very easy question to ask. You want to partition the plane into cells of equal area, and you want to do it in the optimal way. And by optimal, you mean that the average perimeter should be as small as possible. So this is a very old problem. Varro, this is in 36 BC, wrote a book on agriculture. He discusses the bee's honeycomb and says that there are two competing theories about why the honeycomb has 6 sides. One of the theories was bees have 6 feet, and the other was, he says, that the chamber and the comb have 6 angles. The geometricians prove that the hexagon inscribed in a circular figure encloses the greatest amount of space. So this is the isoperimetric property of the honeycomb. So I gave a proof of this in 1999, and then you can ask exactly the same question in 3 dimensions. Now again, you want to partition space into cells of equal volume, and you want to do it in such a way that now the surface area on average is as small as possible. So this has become known as the Kelvin problem, who first worked on the problem and proposed an answer. So by isoperimetric properties, you want cells that are fairly round, but if you make them into spheres to minimize the surface area for the given volume, then you can't pack them together, and so you need some compromise. And maybe you can see the cells that he proposed. So they look very much like truncated octahedra. And let me just show you with truncated octahedra, tiling with them, you can't go wrong. You just put hexagon against hexagon and square against square, and they tile. So, and they're fairly round, so this is a natural conjecture. But Kelvin realized that this couldn't possibly be the answer. And the reason goes back to experiments performed by Plateau in 1849 with soap bubbles. You see here some soap bubbles, and the surfaces are surfaces of constant mean curvature. When the surfaces come together, they always come together in threes, and the angles are always 120 degrees. And when the edges come together, the edges always come together in fours, and they always form tetrahedral angles. So these are the observations of Plateau. And Kelvin's the truncated octahedra don't satisfy these properties, so it can't possibly be the answer. But his suggested solution was just to warp the truncated octahedra slightly, and it's only a slight warping that's necessary so that you precisely satisfy Plateau's conditions, and this became the Kelvin conjecture. So how did Kelvin describe this mathematically? He says it is shown beautifully and illustrated with great perfection by making a skeleton model of 36 wire arcs for the 36 edges of the complete figure and dipping it in soap solution to fill the faces with film, which is easily done for all the faces but one. The curvature of the hexagonal film on the two sides of the plane of its 6 long diagonals is beautifully shown by reflected light. So if we are to state the Kelvin conjecture, we have to make precise mathematical sense of what is meant by the Kelvin foam. And as it turned out, nobody was able to give a precise description of the Kelvin foam in a mathematical sense until the 1990s. And so what we had was not really a conjecture, but a conjectured conjecture, something that if we could make it precise, then we would have the conjecture. So the proof of Plateau's conditions came in 1976 with Gene Taylor. The proof of the existence of this Kelvin foam has never been published. Unfortunately, Fred Almgren passed away the year after the announcement was made that a precise description could be made. In the meantime, in 1993, a counterexample was found to the Kelvin conjecture. This is the Ware-Phelan foam. We might ask, in what sense is this a counterexample if the conjecture itself was only a conjectured conjecture? And so it's really just a conjectured counterexample, not just because it was impossible to state the Kelvin conjecture precisely, but also because the counterexample was constructed by numerical simulations on a computer, and still to this day, there is no rigorous proof of the existence of this counterexample. This slide just, it's a little hard to imagine what this Weyr-Phelan foam looks like. I like to imagine it as formed by a system of tubing, as you see here. There are holes in which you can drop dodecahedra, and then if you slice the tubes into sections and make each of those sections into a bubble and then sort of stretch them out until all the empty space is filled in, then you get exactly this counterexample to the Kelvin conjecture. I was just walking before this talk, and there's a sculpture called Genesis out in front of the Newton Institute by Robinson, and it has interlinking rings that are exactly the structure that you see in the Weyr-Phelan foam. So this was used, for instance, in the design of the National Aquatics Center. This is the counterexample to the Kelvin conjecture. So the lesson is, do not assume that major conjectures are actually conjectures. And I've been corresponding with some of these people, Frank Morgan, Rob Kushner, John Sullivan, to try to state the conjecture in a formal way inside a proof assistant. What I'm thinking about now, and this is not an original suggestion by any means, but I'm thinking about a formal abstract project that I first brought up in the joint meetings in January 2016. There's a big initiative in the mathematics community right now to make a bigger use of formal methods to move things in the direction of digitization. And the point that I think all of us make is that if we promote sloppy platforms, then the entire world will be worse off for it. And the proposal of formal abstracts is just to take major parts of the mathematical literature and state all the definitions in a precise way inside a proof assistant in a way that can be read by ordinary mathematicians and by a computer, and also to give statements of main theorems in the mathematical literature. So, of course, this community is very well aware of the big dangers in writing definitions and stating theorems without actually doing the proofs. One example that I give here with the formal proof of the Kepler conjecture, some of the definitions we had to rewrite as many as 40 times before we got things just the way they needed to be to get everything to work. So there will be, of course, problems with this project in the sense that we're not going to be able to get everything exactly right. But I think this will be a huge step forward in mathematics to get a large body of material stated formally. So at the end, the solution to all these problems is just to do it anyway. So just short term, so this is at a very early stage. We're still just exploring things. My background as a student of Bob Langlands is in automorphic representation theory and p-adic groups. As a sample problem, I thought of just trying to write down the Clay $1 million prize problems in proof assistant. And again, I stress we're not solving a thing here. We're just trying to write things down in a precise way. My background in automorphic representation theory is it's one of these areas that has ambitions to swallow up the rest of mathematics, and there are many subfields that are interrelated with that. So I think even trying to write down what we were doing and talking about when I was a graduate student would already be a very ambitious project. Let me talk a little bit about the Clay prize problems. So there's 7 problems here, and we want to just write them down in a formal way. Some of them are, I think, quite easy to write down, even if they're hard to solve, like the Riemann hypothesis. We just need to say what the Riemann zeta function is. And of course, for instance, in whole light, we already have the analytic proof of the prime number theorem, which uses the Riemann zeta function. And John Harrison, as part of that project, already has the analytic continuation of the Riemann zeta function to the real part of s bigger than 0. So we have the critical strip, and we can talk about the Riemann zeta function. So this, that's very easy. Or the P versus NP. So the official description is given by Cook, and I mean he goes through everything in great detail in the official problem statement. He says what you need to say what a Turing machine is. You need to say what these complexity classes are. He goes through the definition of a Turing machine, and he goes through the definition of the complexity classes. So everything you need for the formalization is pretty much written down there. Poincare conjecture. People have done, you need to say what a manifold is, what a three-sphere is, and what a contractible loop is. There's been a little bit of work, I understand, with manifolds, maybe not too much. People do have 3 spheres and notion of contractibility, so that part is all there. It wouldn't take much work beyond what we have, just to sit down and write down the formal statement of Poincare. The same goes with Navier-Stokes. That's you just write down the partial differential equation, and you have Navier-Stokes. Birch, Swinnerton, Dyer might be a little, so it depends on how much you're willing to assume there. So for many years, the Birch, Swinnerton, Dyer, again, was just a conjectural conjecture because you're using the L function of an elliptic curve, and the analytic continuation and functional equation of the elliptic curve were not known. But thanks to the work of Wiles and the follow-up work on the Taniyama conjecture, you at least have the analytic continuation and functional equation. So if you're just trying to state the conjecture, you need to assume a very, very deep theorem in mathematics to make sense of the question. But if you're willing to make assumptions like that, then it should be fairly doable to write things down. Hodge conjecture, maybe you need de Rham cohomology. People have talked about cohomology theories, but maybe not de Rham cohomology. Yang-Mills. Okay, so this this is where we run into real trouble when we try to state things formally. So my claim is that it probably cannot be stated formally. The problem sort of requires the winner to build a theory and then to prove something about that theory, so it's not really a well-specified problem. So I gave this slide once before at a talk I gave at Artificial Intelligence and Theorem Proving conference, and sitting right in front of me on the front row was, hadn't met him yet, but I certainly met him right after my talk, a physicist who was responsible. If you go to the Clay Status of the Problem by Michael Douglas. Michael Douglas was sitting right in front of me. He said that he thought that a precise statement could be made. Okay, so he wasn't claiming that anybody has stated the Yang-Mills problem precisely, but there are physicists who claim that it might be possible to state this precisely. So I asked just on, if you have a question, right, you send it off to Stack Exchange. So the question is, what is the precise mathematical statement of the Yang-Mills and mass gap problem? A mathematician writing a statement of each Clay Millennium Prize problems in a formal proof assistant. The problem is just, so I've quoted some of the language of the official statement of the problem, and I didn't go out of my way to find the intentionally vague passages to quote. What I'm quoting here is the official statement of the problem. And it uses phrases like in correspondence with. Does that mean there's actually a bijection or some other sort of correspondence? It uses the word predictions 3 times. Are these somehow physics predictions, or are these precise mathematical conjectures? It says, as it should agree with the predictions as described in textbooks. And then there are no references to any textbooks. So my proposal to, if you want to collect $1 million, is to write a textbook. And then quote it as evidence that you've correctly solved the problem. So I got a few suggestions, nothing definite. The last comment was a little bit pessimistic, that Jaffe and Witten's statement of the problem is probably the most precise that you can get with our current state of knowledge. So in conclusion, what I'm suggesting is that we sort of move into mathematics in a bigger way, stating definitions, statements of conjectures, statements of theorems, but that this will often not be as easy as we think it might be. Where we think that we have conjectures, we may find that we only have conjectures of conjectures. Where we think we have theorems, we may have statements that are so vague that we can't possibly formalize them. And in doing this, we will start an interaction with the mathematical community that I think will benefit everyone. So thank you very much.
So thanks a lot. That actually mixed formality and humor in a way that was quite unexpected. So I'll open it up for questions. You know, when you just raise your hand, I'll keep track of who's asking questions, and please state your name before you ask a question.
I'm Arnold Neumeyer from Vienna.
Yes, okay. So another expert on Yang-Mills.
This Clay problem on Yang-Mills and mass gap is in fact a conjecture problem only because it's really vaguely formulated. But I believe it can be made precise.
Yes.
and it's all that stuff that is mentioned in textbooks is of course in physics textbook in a very non-rigorous way, but there is a lot of mathematical physics behind in the background that I think one can make a precise statement.
Yes.
What is meant.
Okay, so I should say that as I've explored this question, Arnold's name comes up again and again as somebody enforcing the rigor of the Yang-Mills problem. So good to have you here.
So one thing that struck me is that the way you are going about this, it sounds like just defining things precisely could actually create new mathematics as well.
Yes, so this has been my experience, for instance, with my interaction with the geometric measure theory crowd trying to precisely formulate the Kelvin problem. We haven't written anything down precisely because, as soon as you start asking these questions, research questions start coming up as well.
My name is Tony Hoare. I suggest you need a theory of bubbles in order to formalize it accurately.
Okay, thank you.
So there is a theory of bubbles, right?
Well, there's the subject of geometric measure theory deals with bubbles. Yeah.
Okay, so I need to see some hands out there. Yeah, we have plenty of time for discussion, and I think there's topics. Yeah, Steve, here.
I'm in the F abstract. I'm
Name,
Steve Audi. Would you like me to stand? I'm Steve Audi. Tom, in the F abstracts proposal, are you proposing from here on out, going forward, that we try to formalize the statements and even definitions of current and new mathematics, or also a more ambitious project related to our discussions yesterday would be to go back and formalize the existing body of mathematical theorems and definitions? What the F abstracts project specifically, which of those goals is, do you think, part of that project? Thanks.
Well, we're not going to get everything. I mean, mathematics is growing too rapidly for that, but like here I'm starting with big conjectures. Let's start with big theorems and move in the direction of less consequence.
So it's neither new nor old, but kind of from the hardest problems downwards. Okay, Tobias.
Tobias Nipko from Munich. Well, of course, the F abstracts project raised the thorny question of what is the language and logic going to be that you formulate things in.
Yes?
Okay, you did say you're not going to answer open questions.
My proposal is lean. I'm based in Pittsburgh, and a lot of development going on there with lean. I've used whole light in the past, but I don't think it's really suited for. It's very good for real analysis, sphere packing is the type of things I've done, but foundations are a little bit weak.
What about set theory?
I've thought about set theory, but it's tempting.
My name is Freek Wiedijk from the Netherlands. So to react to Tobias, I would like to see it as some kind of competition, do it in various systems and see what turns out nicest. That's my angle. My question is, once you get one of those formal abstracts, what are you going to do with it?
So this is part of the initiatives of this nonprofit, IMKT, was just set up to manage mathematical assets. I mean, this will just be released on the web under liberal license for anybody to use it in any way they want to use it, whether data mining purposes or mathematicians looking up definitions or as a research tool or whatever.
So Tom, I have a question actually. Looking back on the FlySpec project, are there any lessons learned that you'd like to share with us? Anything you might have done different?
Do it all in one proof assistant would be one piece of advice. It was very valuable early on to have the contributions in Isabel. Those were the first parts that were completed, but it turned out to be a minor nightmare to reconcile. So in the end, there was one statement that was done in Isabel that needed to be imported into Holite, and they're just slightly different conventions in the two systems that made it a bit of a nightmare to reconcile everything to get one coherent theorem in the end. So that's one piece of advice.
Yeah, you like it.
Hello. So outside of research mathematics, in industry, one of the tasks of formalization is to take imprecise regulatory requirements and to formalize them. So the Yang-Mills problem here is a very standard problem in industry. Do you know of anyone doing anything particularly creative with that? I mean, my understanding is at this point, the best you do is you translate it and then you discuss with the regulator whether your translation meets their requirements.
So I don't know specifically, but the experts are here. So
Yeah, but I think that's a good. That's a so the question is in formalizing informal requirements. You run into the same problem, and I think the connection you make to Lakatos. I think there's a similar dialectical process about maybe arriving at formal statements of these terms as well. There's going to be counterexamples and new definitions and responding to those. Wait, let's see. I think Fenner had a question, and then.
I'm Fenner Tanswell. I thought my question's also about the Lakatos because he's clearly on the money with some things, as you give examples of the proofs and counterexamples and things like that. But when you read proofs and refutations, there's also this strong skepticism about formalization, especially the introduction is like against the dogmatists of mathematics and things like this. And I guess what I'm wondering is whether you see what you're doing with the formalization as kind of suggesting that Lakatos is wrong about some of those skeptical aspects.
So I'll just go back to my first slide. Keep your conjectures bold and your refutations brutal.
There's a hand up at the back. Yeah.
That's Adam Krkiewicz from Glasgow University. I wanted to ask, what do you think is the right venue for your project, for the formal abstracts? Should it be a GitHub repository or a journal submissions?
Yeah, I think we'll just put everything on GitHub.
You got a project yet?
No.
And Randy Ollie, you didn't hear you say it, but I guess you mean that this formal abstracts, all of them should be based on the same authentication. It's not as if you want to define this abstract and that abstract. They should have the same underlying definitions, which would be, number theory and analysis. It should all be built up in a single way. Is that what you have in mind?
Yes, I think we'll pick one foundational systems like the calculus of inductive constructions in Lean, build everything up from there, and if people want to translate, then people can translate.
So it's the second time you mentioned lean, which I played with a bit, but it's a very new system. Is there some reason for choosing that? Constructive, intentional, but this isn't maybe not a standard choice.
So we would use classical logic. It's a new system, and that has its problems. Things are still experimental. Things are changing and developing quite rapidly. So that might be a bit of a difficulty.
Okay, one last question, Peter.
Peter Leffley, Lumsden. One of the things that we saw from your example of the Kelvin conjecture was how even stating something precisely can already depend on a hard theorem. So wouldn't this make a danger that sort of formalizing abstracts would become as hard a problem as formalizing all the theorems themselves?
Well, if we can't formalize Yang-Mills, then we won't formalize Yang-Mills. I mean, we'll just do what we can do.
Okay. So one last question, the gentleman in the back.
Prathamesh from Institute of Mathematical Sciences, Chennai. One question I had is, what kind of interest do you see among mathematicians in like experimentally done census? Like just you mentioned about census of tilings. This is like census of, for instance, like hyperbolic manifolds, like which are experimentally carried out.
I'm sorry, I'm having a hard time hearing.
So there are various kinds of census problems in math which are experimentally carried out. For instance, the hyperbolic manifolds, three manifolds and stuff like that. So do you really see like an interest in the mathematical community in actually informally verifying these experimental results?
So the question, as I understand it, is whether there's interest in the mathematical community in verifying, formalizing experimental mathematics. My impression is that would be difficult to do, but if there are ideas about how to carry that out, I think they would be welcome. I don't know anything specific.
Just mentioned like the case of hyperbolic manifolds, for instance.
Yeah.
Done by this thing called SNAPI by Jeff Bates, but like there's been no formalization in these aspects.
Yep.
Okay, so let's thank Professor Thompson.